This is Premier Aerodynamics Podcast number 25, and today we're talking about the dimples on an airfoil leading edge. So these dimples, they're effectively like golf ball dimples, and we're looking at this paper called Study of Leading Edge Dimple Effects on Airfoil Flow Using Tomographic PIV and Temperature-Sensitive Paint. So what they were looking at in this paper was an airfoil, a NACA 0015 airfoil. So this is a symmetric airfoil with a 15% thickness to chord ratio, so it's a fairly thick airfoil. And them and a lot of other researchers have looked into how the effects of dimples on the leading edge affects the flow separation patterns. And one idea of how they work is that these dimples, they create these vortices, so they're effectively vortex generators. And they think they have this idea perhaps that under certain configurations, these vortices are going to re-energize the flow and keep it attached and so on, like a general vortex generator does. And so they looked into this airfoil, and just summing it up before we go into the details, they looked in at the abstract. It says airfoil blades can experience a significant change of angle of attack during operation cycles, which may lead to static or dynamic stall in various applications. It is unclear how elements distributed at the leading edge would affect the aerodynamic performance of stall behaviors. In this present study, a distributed dimple configuration was investigated and compared to a baseline smooth NACA 0015 airfoil at low Reynolds numbers. Now they used PIV and temperature-sensitive paint, which is pretty cool. The temperature-sensitive paint is a fairly new technique, and we'll talk about that a bit later. Continuing on the final results, the results suggest that distributed dimples create an abrupt separation leading to stall and induce a similar stall compared to the smooth model. However, the stall is induced more abruptly and with different flow patterns. Results show that patterns of separated shear layers as stall conditions were enhanced by the current configuration. So in other words, putting on dimples onto the leading edge for this particular case actually was worse for stall. You get a more abrupt stall, and it was actually at a slightly lower angle of attack. And this is one of the earlier papers on this. It was published in 2019, and there's more work being done on it all the time. And so they're just trying to figure out what should work. So as I mentioned earlier, they use temperature-sensitive paint, and that's pretty cool. So what that is effectively you paint a surface and you heat it up, and then you get a camera which can see infrared or whatever you configure, whatever wavelengths you want, and you can see what the cooling of the surface is, and based on the cooling, you can determine what the flow speed is, the shear stresses on the surface are, and then you can figure out whether something is still attached, detached, whatever. So you don't see too many papers with temperature-sensitive paint, so TSP. So I'm quite excited that they do have it in this paper. So let's move on to what they did, the details. We know that it didn't work out too well, but why didn't it work out and what were the effects? So in the introduction, they say a variety of airfoil surface degradation can occur, such as peeling paint, erosions, icing, bug, debris, dirt accumulations, protective barrier coating, peeling, and so on, depending on the application. Degradation inevitably occurs over long-term airfoil operation. If degradations are sufficiently large in size, they may cause significant power loss. On the other hand, similar degradation elements, either passive or active, can lead to improved airfoil performance. For instance, active control mechanisms such as dynamic pitch, plasma actuators, and synthetic jets have been demonstrated effective in stall control, which enhances airfoil lift generation under certain large angles of attack, and therefore increases the overall power production of the rotor blades. However, the active methods are typically not cost-effective and require relatively complicated materials and structures. Hence, the passive method of delaying stall is another important method that requires further investigation. So just to determine what the active versus passive is, for those who don't know, active is where you need to effectively impart some kind of energy or feedback or whatever into the system for it to work so it can move around. Passive is where it can't really move. It's just you stick it on and whatever geometry it has, and when you stick it on, that's how it's staying. So one major advantage of active is that you can tailor it to the conditions that you're in, whereas passive is really just one size fits all. So active, usually you will get a much better overall effect, but you need to put in energy and so on, and it becomes more complicated and it can break easier. So there are advantages and disadvantages. It is still unclear, back to the paper, it is still unclear and debatable how large distributed elements on the leading edge affect the aerodynamics at high angles of attack. In fact, The effects of distributed leading edge structures would have important implications in the real world operation. Effects of geometry, thickness, and size of the leading edge disturbances have been reported. Distributed at the leading edge, these structures may stabilize, modify, or intensify the growth of Tolman-Schlitting waves, leading to delayed or advanced transition from laminar flow to turbulence. So this is a very important aspect for boundary layers. So Tolman-Slitting waves, which are often called just TS waves, they are one way of a boundary layer of transitioning. So there's like a gambit of ways and leading from very small disturbances to very large disturbances. So very small disturbances are disturbances where the boundary layer has a disturbance and it's so small that you'll actually get damped out and you won't transition to turbulence. Very large disturbances is where you have something called bypass transition. So you have this massive disturbance which just jolts the entire boundary layer into just being turbulent. It just creates all this turbulence out of nowhere and you're now turbulent. Tolman-Slitting waves, TS waves, they're sort of in the middle where you have a disturbance and then it starts to grow and it's sort of like this wave. So imagine like if you've ever seen like cigarette smoke, it's not exactly the same as this, but it's a good way to visualize. If you ever see cigarette smoke coming off of a cigarette and it goes up fairly laminar and then it starts to get quite wobbly, it's kind of like that. And sometimes you can see it depending on in a boundary layer, depending on the lighting and everything and what fluid you're looking at, but usually you can't. So this is what happens. You have this TS wave starting and then it starts to break down and it breaks down three-dimensionally and then you get turbulence and it creates a turbulent boundary layer. So that was just a little side note for how boundary layers transition. So back to the paper. It is also unknown whether certain passive flow control methods, such as distributed dimples used on golf ball surfaces, would help prevent the stall at large angles of attack. To fill these gaps, we investigated the effects of 3 different types of distributed leading edge elements, including dimples, bumps, and 2-dimensional bumps on the stall behavior of a stationary NACA 0015. That was in a previous paper. In this paper, they're looking further into the dimples. And again, they use temperature-sensitive paint, which provide a quantitative measurement of the separation regions and turbulence levels in the leading edge and within the dimple regions. So let's talk about their experimental setup a little bit. In this study, models used in our previous investigation, so in this paper, which is open access by the way, you can access it, I've put the link in the description, with smooth and dimpled leading edge surface conditions were tested. Both models have the same basic geometry of NACA 0015 with a chord length of 135 millimeters. A smooth airfoil was used as a baseline, referred to as smooth. On the second model, hemispherical cuts were made into the surface, so these are dimples, and they were evenly distributed up to 20% of the chord from the leading edge, and they're in a staggered pattern. These dimples had a diameter of 5 millimeters and a depth of 2.5 millimeters, resulting in a roughness depth to chord ratio of 0.0185, so 1.85% of the chord. Both models were precisely fabricated using 3D printers with acrylitrile butadiene styrene, so ABS plastic. That's a very common plastic for 3D printing. I don't usually say it out loud. I like the full name is just ABS plastic, everyone says. They were printed in 2 symmetrical halves and glued together. The model surfaces were carefully polished and treated with acetone vapor to remove spurious features and leading edge gaps. So this is really cool. ABS, when you print anything really, you have usually these tiny little layers and you can see these lines. Now, depending on your application, that's fine. Most applications for aerodynamics is not, so you want to get a smooth surface. You can either sand the object, which has some benefits. Here they use acetone vapor. So acetone vapor will actually dissolve the surface a little bit. And if you do it correctly, you can get a very smooth surface without eating into the surface too much. Now, one thing that is interesting, which they don't really go into here, is how this affected the trailing edge of the wing, because the trailing edge is very sharp. If you're dissolving some of the plastic, that might affect the trailing edge. I assume that it's okay because I haven't gone into it, but I don't know. It should probably be okay. And for those who are watching this on YouTube, they have this figure here, which shows the test models with the dimple geometry details. For those who are listening to this, the dimples look very much like a golf ball. So that's what they look like. And they're both on the suction and leading and pressure suction and pressure sides. so the bottom and top sides. So going a bit further into how they use the temperature sensitive paint, I just want to cover this because it's fairly cool. You don't come across this too many times. Temperature sensitive paint was set up to perform surface measurements in the leading edge region. The TSP, the paint, can give accurate measurements on the separation regions due to the differences in heat transfer in attached and separated regions. The model was heated up to 10 degrees above room temperature, and the wind tunnel was run to obtain a wind-on image and capture those differences. So when you put the wind on, then it starts cooling, and you can see the cooling rates of the different surfaces, different parts of the surface at least. Onto the result and discussion. At low Reynolds numbers and angles of attack, it is recognized that a separation bubble promotes laminar to turbulent flow transitions at the leading edge, and this facilitates the turbulent layer reattachment and contributes to the higher lift at low Reynolds number airfoil. So let's talk about this. I've talked about laminar separation bubbles quite a lot in podcast number 11. So if you want, go check out that. It's called NACA 4412 laminar separation bubble. But let's talk about a little bit here what a laminar separation bubble is, or a separation bubble in general. So what this is you have the flow going over a leading edge, and it's laminar. Then it detaches, and then in that detachment region, when it's flowing over still, it will transition to turbulence and then reattach. And in that detachment region, you get this recirculation bubble. Now, they talk about here that it contributes to the higher lift at low Reynolds numbers, and this is true. So when you have a laminar separation bubble, this effectively increases the thickness and the camber of the wing, so effectively pushes the angle of attack higher in practice. So the thickness of the airfoil still stays the same, the physical thickness, but because you have this laminar separation bubble above it, you get a slightly extra thickness and an extra camber. So that acts as a thicker wing, which will produce more lift, and you also have a camber, which is effectively like pushing it to a higher angle of attack. So that's why laminar separation bubbles are good at increasing the lift at low Reynolds numbers and low angles of attack. However, the burst of separation bubbles, coming back to the paper, at high angles of attack is the reason for a sharp decrease in lift and increase in drag for a leading edge type stall. So what they're saying here, which is true, when you have this bubble, you have a higher lift, and then if you burst, you not only get the drop in lift because of separation, you also get the drop because now you have a lot of thickness as well. You had a higher lift. So it's a double hit kind of thing. And you get an increase in drag as well. And they also talk about leading edge type stalls. So this is quite a dense part of the paper, it seems, where there's quite a few different parts to talk about. So leading edge stall, let's talk about that a little bit. So depending on how thick your airfoil is, you're going to have different stall patterns. If you have a very thin airfoil, like a NACA double, let's say it's 2% or 3% or whatever, then you're going to have stall starting from the leading edge, and the entire airfoil is going to be separated very quickly. So it's almost like instantaneous when you push it to a certain angle of attack. As the airfoil's thickness increases, this stall starts at the trailing edge and it moves up. So it's a more gradual stall. So that's what they mean here by leading edge type stall, when you have stall starting from the leading edge, and usually that's very catastrophic, where the entire airfoil just stalls at once instead of little parts of it stalling, and you're still producing a little bit of lift. So as the Reynolds number and angle of attack increase, the reattachment does not occur for these separation bubbles. It detaches and then it just won't reattach, and that's why you get a lot of stall. The existence of leading edge elements or structures are found to have significant impacts on the stall angle as well as the mechanisms of the stall. As shown in figure 5, which is a figure here reproduced from a paper. For those listening, it's from what I can tell, a PIV image of this airfoil at different angles of attack, and it's showing stall for an airfoil with dimples compared to a smooth airfoil, and the one with dimples stalls at 1 degree lower than the one that's smooth. The distribution, back to the paper, the distributed three-dimensional dimples actually slightly advance the stall relative to the baseline model. Meanwhile, the dramatic change between 14 degrees and 15 degrees and the large slope of the separated shear layer resemble the features shown in the smooth case, indicating the leading edge type stall, even though the dimple disturbances have been introduced. However, the thickness of the separated shear layer is obviously greater than that of the smooth case, This is caused by a wandering shear layer in the dimple case as a result of disturbance-induced instability. Depending on the Reynolds number and the dimple dimensions and configurations, various investigations have reported a variety of vortical structures within the dimple cavity that contribute to the boundary layer disruption, separation, and recirculation patterns, and a decrease in drag in the turbulent boundary layer. So this is interesting. Depending on how you have these dimples, you can get different vortical structures forming in them, and this greatly affects all the flow patterns across the airfoil effectively, including the drag in the turbulent boundary layer. So that's quite interesting. At low Reynolds numbers, the flow streamlines become curved on the dimple surface, and the flow separates near the leading edge of the dimples and forms a recirculation zone before reattaching. So in other words, these little dimple regions, they're effectively in separated regions. They create a separation before you hit them effectively at the leading edge, and then they're all in the separated region. Maybe some recirculation is going on, who knows, and then it reattaches. So before we go any further, just want to say, check out everything we do here at Premier Aerodynamics. Check out the experimental instrumentation we do, the Atmosphere Hawk, PRV systems, and traversers we make. Check out the courses we put on to make you a better aerodynamicist. We put on CFD, experimental, and theory. And check out the International Aerodynamics Conference, which is a conference we put on every year, so you can get together and talk about aerodynamics with other aerodynamicists. So check all of them out. Links are in the description. So back onto the paper. They go, besides the compression bubble in the leading edge of the airfoils, the dimple pattern generates transition/turbulent bubbles in the dimple location. It is also apparent that the flow pattern before the separation region is quite different from the smooth and the dimple case. The dimple case obviously offers a much abrupter separation. This is evidence of dimple influence in boundary layer pattern. These mechanisms could be related to the particular staggered pattern and depth of the dimples. Exploration of boundary layer patterns and distribution methods would need to be investigated using a closer view on the dimple cavity and for several dimple characteristics such as staggering pattern, dimple size, such as those on the flat surfaces. So what they're saying here is that these dimples, they are creating a different type of transition and turbulent bubbles, and they're effectively affecting the boundary layer transition and the separation. And then they have a whole bunch of different figures. They're just like tiny little details. They're not that interesting to go into. Let's go into the temperature sensitive paint. So the image of the temperature in degrees Celsius. So they have the image here. And for those who are listening, what this image looks like is effectively, think of this plane surface. The bottom half is smooth, the top half has dimples. And from about a quarter away from the top, it's very yellow, and then above that you get a change in color. So you have green, blue, dark blue, pinky, violet. And so what this is showing is that at the leading edge, you have a very great cooling rate. Over the rest of the airfoil, it starts to become less and less. These colors dictate the cooling rate. So you can see where separation bubbles are, how fast the flow is going, and so on. So they say the image in temperature shows a change in intensity occurring in the leading edge region towards downstream, indicating separation after the second row of dimples. It is noteworthy that this paint map and line profile show hotter regions inside the dimples, indicating higher temperature and heat transfer, thereby indicating higher transition turbulence regions consistent with flows in cavities where recirculation and separation often occurs. So what they're saying is in these dimples, it's actually still hotter, which means that you're not getting as much heat transfer. And that's likely because there's not nearly as fast a flow going through it. So the shear stresses are lower, the velocity is lower, and this is expected because effectively, in order for the air to go in, it needs to take a dive down and then come through, whereas opposed to it's expected that the flow is just really going to zip across the top, and inside these dimples, you're going to get a lot of recirculated flow. So that's fairly expected. So in conclusion, used as passive flow control devices, dimples, however, are not good at preventing separation if distributed on 20% of the leading edge, according to the current results. It is worthwhile to further investigate whether these dimples would help improve stall if placed on other locations and under other regimes, as suggested by favorable results of previous vortex generator research. The presence of transitional / turbulent bubbles in the vicinity and within the dimples. So this is what these results showed, that in these dimples and in the vicinity of them, you get these bubbles pretty much everywhere. So I'm guessing that these dimples are probably breaking down this turbulent bubble into many smaller bubbles and probably localized bubbles. So that's the end of this paper. Make sure to check out everything we do at Aerodynamics. Make sure to like and subscribe this. And thanks for your attention, and peace out.